So quantum technology is the general field, and then one can cluster it in different pillars, right? One is quantum computing, one is quantum communication, one is quantum sensing, and I would say quantum foundations should be also one of them, right? And we are more on the quantum sensing and the quantum foundation aspect of the quantum technology. Basically, we want to observe quantum phenomena of larger objects. So we know that quantum phenomena are part of the recent revolution in quantum technology, where you can basically generate quantum states, non-classical states, and do something what you cannot do with classical processing. So for example, you can build a quantum computer, or people try to build a quantum computer, yeah? And they base their research on certain hardware, like atoms, or superconducting circuits, or photons. But we are interested, can one do this also with larger objects? Yeah? And in our case, the objects are of the size roughly the human hair, the diameter of the human hair. They are called mechanical systems, so they are small vibrating things. Yeah? And this we basically do in these two labs. So in one lab, what we do, we levitate objects, yeah? Because this is very important. Quantum phenomena are very fragile. So you have to isolate your system as much as you can from the environment. And actually the best you can do is to levitate it. Yeah. This is what we do in one of the labs.
So in this cryostat, right now, we are colder than outer space, which is around minus 270 degrees Celsius. And we need this in order to get the superconducting effects that we want to levitate our particle.
Levitation can be used in a couple of ways. So we're interested in doing two things in this lab. So one is trying to generate quantum states of macroscopic objects. And in order to do this, you need to stop your object that you want to make quantum from interacting with its environment. The interaction with the environment creates something called decoherence, which completely destroys any quantum states. This is one of the reasons we don't see quantum effects in everyday life. So that's easier to do with smaller objects, but you also need to remove all these interactions, which include things like air molecules bouncing off the surface of the sphere. So we need to put these objects in something called vacuum. And we also, by cooling these objects down, we can also reduce these interactions as well. So the cryostat we have, it both cools the objects down and pulls away all the gas molecules that allow us to try and make these quantum superpositions. The other thing we're interested in doing with these levitated particles is sensing. Because they're levitated, they are incredibly sensitive to external forces interacting with them. I can demonstrate that on this graphite sheet here, by if I just blow with my mouth, we can see the graphite sheet move around. Okay, so it's incredibly sensitive to these external forces. The kind of things we're interested in sensing are some new fundamental physics. So one example of this is dark matter. So we're very sure it exists, but we don't know what it's made up of. So in order to determine what it's made up of, we can build experiments on Earth that can maybe interact with the dark matter that's flowing past us right now and tell us a bit about its microscopic nature. And we can use levitated particles for this.
So Tom showed you the levitation at a very microscopic scale, so this large sheet. But if we want to achieve any kind of superposition, we need to go a bit smaller. But smaller is still pretty big. So if I were to compare the particle that we use, which is a 50 micrometer in diameter, which is around the thickness of a hair, if this would be the size of an atom, then the 50 micrometer particle that we use would be the size of Gothenburg. Even though both are very small for us, there is still a universe between them. So this is nice. We have our chip with our particle. We put it in the cryostats. We cool it down to really low temperatures. Then we can make it levitate by sending currents inside the coils, the really small coils that are on there. but then we need to see it, right? We need to see if it works. Here it's easy, we're outside of the cryostat. But once we're inside, what we did is that we have an opening in our cryostat, which help us see through all the way to the center and all the way to where the particle lies. And we have a video of this that I can show you. So what you're seeing is a top view of the chip, right centered right where the particle lie. The particle is lying there. It's a 50 micrometer lead particle, which is a superconductor. But once we start sending current in the video, you'll see the particle will start to levitate. There it is. The particle levitates, which is really nice. It was what we wanted to see. But then you see that there's still a lot of vibration, and at some point it just falls back down. Well, the problem is that to record this, to have a video of this, we need to shine lights in the cryostat. And if you remember, we need really low temperatures in there, such that we have the superconducting effect. And shining lights is energy. It's heat. So we're actually heating up the particle. So if I show you again, the particle is now cold, it's levitating, so now it's not on the chip anymore, and it's being heated up by the lights that we send to see this video. And at some point, it's heated up so much that it breaks superconductivity. It doesn't expel the magnetic field anymore, and it just falls back down on the chip. So this was a nice way, this nice proof of concept to show that we can do levitation, but this is not the way that we can go to the superposition states that we want to see. Because we want to do the opposite of heating it up, we want to cool it down. And we want to cool it down until we have no more thermal energy on the particle, and hopefully then be able to see any quantum effects or not.
I think one thing is long-term motivation. That's very important. So to have a vision, a goal, what you want to reach in research. And this, in our case, is really long-term. So it's 10, 20 years. It will take so long, yeah, because it's very hard. Nobody has done it. And this drives me, yeah, to some extent. The other extent is that you usually in research, most of the time it's failure. So you do something, it doesn't work. You do something, it doesn't work, yeah? And then one has to enjoy the moment when it actually works, right? And this is just fantastic. You reach something, yes, now it works, and then we can build up on this and go further, right? And the good thing is that with the group, it's wonderful to discuss about physics, right? How do we do this? Why doesn't it work? What could be possible ways to improve this? And this is, I think, a big part of science, to discuss with each other, and basically one has to like it. Yeah. And in the lab where we are currently here, we have a different type of systems, basically mechanical resonators, clamped mechanical devices, which we fabricate here in our clean room. And they are a bit larger than the levitated ones. One can actually see them, yeah, with your eye. And there we try to interface them at some point with single photons.
To talk about optomechanics, let's start with optics. So in the daily life we have bulbs and sun and all this light sources that emit the light of the different colors and auto-synchronization. So the lasers is the opposite of that. It's monochromatic. So meaning that they emit at a certain wavelength and they're coherent. So I would say the analogy to this would be the crowd talking all at the same time, or a choir singing the same note. And so the laser that we see here will be from 1510 nanometers up to 1620. And this range is out of our vision. So when you think about wavelengths, the short one is blue color, the long one is red. And if it's even longer than that, it becomes invisible. So that's invisible light. And we choose telecommunication wavelength, so 1550, because it's a sweet spot for the optical fibers. These are all this yellow, white, no, it's not cables, it's optical fibers that transmit our laser light from the light sources to the setups. and it's stable and precise. So we use it for the measurements. That's the optical part. So now we know what is the laser light, and if we build a cavity, meaning that we place two mirrors facing each other and put the quant of light, photon, inside, our photon will be trapped inside the cavity. So the reflection will be coming on one mirror and reflected back and forth, enhancing the light field inside the cavity. And this will be the case until the photon is leaving the cavity. And how long the photon will bounce between two mirrors will be defined by the reflectivity of mirrors. And if the reflectivity is high, then that would be called high finesse cavity. But in our laboratory, we use the thin films and we fabricate them in our clean room. And here are some examples of them. So this would be very thin 20 nanometer silicon nitride membrane. And on that we pattern photonic crystal as we design. And then we place this at the end of the cavity, as we will see here. And as I just described, we have the laser coming to our device, reflect back, and then it carries the information about the mechanical state of the system. So what we can see there, here is the frequency of the mechanical resonator. So now it's about 700 kilohertz. And then here I locked the cavity. And what it means, I try to stabilize how I sense the position. But as you can imagine, this membrane is super sensitive. And if I just do this, I disturb the system. And what we do in order to combat this, for instance, it also should be the case if I just start to walk around, but it's dumped. And it's dumped because our optical table doesn't allow the propagation of my footsteps to the mechanics because it has the air legs. And in a nutshell, it's a massive plate floating in the air just to not let the propagation of the vibrations to our system. That's one thing. Another thing is that our 20 nanometer silicon nitride in the air will be by no means a good sensor if it will be in the air. So that's, we put it in the vacuum. So this is a vacuum chamber, which has two pumps. One will be the turbo pump going to 10 to the minus 7 millibar. But then additionally, we have the ion pump that pumps down the system to the minus 9 millibar. And this vacuum is almost as the space-like, so like between the planets. So there is no air around the membrane, just to make sure that nothing collides with our mirror. And then when we want to build an optomechanical cavity, we can, for instance, look at this setup where we have the same membrane and the fiber that will act like the end of the fiber, optical fiber that we use for the laser, and then in the end there will be the mirror, and then this will be our described system, the optomechanical cavity. And what we care about in the mechanical part of this mirror is that quality factor and the oscillating frequency. So we already saw the oscillating frequency, that's just defined by the design, but the mechanical quality factor, easy to understand it if you imagine the guitar string, and if you excite it, it produces a sound, and you want the sound to propagate and last for a long time, so you apply more and more stress to the string. And the longer the sound lasts, the higher the quality factor of this mechanics. So that's what we engineer here. We engineer mechanical quality factors above 10 to the 8th for the frequencies of some megahertz. And these requirements are for certain regimes of optomechanical systems.
I think people are driven really by curiosity. So they want to do something what has not been done, yeah, and what promises to lead to something new or undiscovered, like extending or bringing larger and larger objects into quantum states, yeah, that hasn't been done. Yeah, it's not clear if there's a boundary. And I think but has to see where it goes. I mean, a lot of people are super interested in quantum technology. It's a lot of promises, what this technology can do, what we currently cannot buy. Yeah? And on paper, it should do amazing things. But it has to be seen. And this requires still research, how we can basically build, engineer, understand these systems such that we can control them and use them so that the environment does not disturb them. So this is very hard.